All right, so this is the second and last lecture in Chapter 8, and this will be about periodic properties. So just as a reminder, what we mean by periodic properties are those properties that appear on a periodic basis with the elements as they're arranged in our periodic table. And just as a reminder again, so the elements that are in the same group or family, that is vertical column, have similar properties. And the three periodic trends that we will focus on are atomic radius, ionization energy, and electronegativity. One very important aspect of learning about periodic properties are being able to explain why the properties are the way they are. And that's typically what most students struggle with most. So I decided to start with the explanation rather than the trends. All of the periodic trends we're going to be learning about can be explained in one of two ways, either with a phenomena we call effective nuclear charge or by way of the shielding effect. So I want you to keep these two phrases in mind throughout this lecture and make sure that if you were asked why as to the properties of any of the periodic properties I talk about, that you could explain the why using either one of these two features. To elaborate just a little bit, when I talk about effective nuclear charge, I am talking about the degree of attraction electrons feel for the nucleus. Of course, since the nucleus is positively charged with protons, it's going to draw in or pull or feel attraction for the electrons. And the stronger this attraction is, the higher the effective nuclear charge is. Just as important to keep in mind is that the electrons that make up the core, the inner electrons, not the valence electrons in the outermost shell, but the inner electrons, shield the outer valence electrons from feeling the full attraction of the nucleus. And that ends up being an important feature in explaining also. Effective nuclear charge is approximately equal to the valence electrons an element has. Okay. So, that doesn't write very well, does it? So to be a little bit more specific, let's imagine we were talking about a phosphorus atom. Phosphorus is in group 5A, so it has 5 valence electrons, and so its effective nuclear charge would approximately be 5. To explain this, which I'm not going to hold you responsible for, but if you're mildly curious, so the effective nuclear charge for phosphorus, if there was no shielding, would be 15, right? Phosphorus has 15 protons, so you would feel, okay, electrons should know there is a pull of 15 positive protons. No, not the case, because all of these core electrons kind of make a shield around the nucleus so that the outer electrons, the one in the highest energy level, the valence electrons, don't feel the full attraction because of the repulsion from the inner ones. And so how many inner electrons are there? There are 10 altogether. So if you subtract those 10 inner electrons, you end up with a net nuclear charge or effective nuclear charge of only 5 for phosphorus. So that's how we get, but for our purposes in this class, you can know the number of valence electrons an element has, and that's its approximate effective nuclear charge. All right, so what are the trends of effective nuclear charge? Effective nuclear charge increases from left to right across a period. That's a horizontal row, right, on the periodic table. You can think of it and help you memorize it as you know that the number of valence electrons increases left to right, and remember that effective nuclear charge follows valence electrons. That may help you. A more explanatory way to remember it is that as we're going left to right across a period, the number of protons increases one by one by one, and therefore the attraction or effective nuclear charge also increases. On the other hand, effective nuclear charge decreases going from top to bottom down a group. This is primarily because with each step down a group on the periodic table, you are adding an additional energy level for the electrons. Every added additional energy level puts the valence electrons farther and farther away from the nucleus. So, of course, those valence electrons are going to feel less attraction for the nucleus. And that's actually a more profound effect than it is moving left to right across a period. There are a lot of ways to kind of get you to imagine what shielding is. But one way, imagine your favorite band is playing in center stage and you didn't have the money or you didn't get tickets in advance enough, so you're stuck way in the back. So you don't have the full attraction or full effect from that band if you're way in the back, because you are shielded by all these people in between the band and you. Same thing with valence electrons. Valence electrons don't have a front row seat to the nucleus. So let's talk specifics. Let's talk atomic radius. What do we mean by radius? Well, basically radius is the distance between the nucleus of an atom and the outermost electrons, okay? Just like the radius of any circle or sphere. So when you read atomic radius, I want you to simply think of size. It is a measure of the size of an atom. And there are trends. There are predictable periodic trends for the size of the atoms. Here are two different pictorials for the trends in atomic radius or size of an element. And so I want you to do two things. I want you to pick a row or a period and look from left to right and decide what you think the trend is for size, and do the same going from top to bottom. Whatever graph is easier for you to visualize. One thing that's usually counterintuitive is that look at the size going left to right across any period. I would think most people would guess that the size increases because you're adding stuff to the atom as you go left to right. You're adding electrons, protons, neutrons, what the heck. But it turns out the size of the nucleus has really nothing to do with the size of the atom. What determines the size of an atom are where the valence electrons are. That's the outermost part of the atom. So look carefully going left to right. Size decreases. Okay, and this is not good. I need to get a new stylus. All right, so size decreases going left to right across a period. And as you might expect, size increases going from top to bottom. That's no surprise, right? You're adding energy levels as you go from top to the bottom, so of course the electrons are getting farther and farther away from the nucleus, and so the size of the atom increases. This left to right trend is the one, be real careful because that can trip you up. To give you an idea of the difference in size going from top to bottom down a group, let's look at group 1A and let's compare lithium and sodium. No surprises here. Sodium is farther down in the periodic table and is much larger, so I think visually it'll be easier to see. So on the left we have a Bohr model of lithium, and lithium has two energy levels, 1, 2. So its atomic radius would be represented with a vector from the radius to the second energy level. Sodium, on the other hand, has 3 energy levels, 1, 2, 3. So its radius would be represented, a vector going from the nucleus out to the third energy level. So those additional energy levels add a great deal of size to an atom. So that explains the trend going from top to bottom down a group. So take a minute and look at a periodic table and decide what's larger. This would be a typical multiple choice question. What's larger, lithium or fluorine? So if you look at a periodic table, in case you're too lazy to pull one out, you have lithium over here in group 1A, and then fluorine is in the same period, but is over in group 7A. So which one is larger and why? Well, if you listen to the earlier slides, or if you understood them, a lithium atom is larger, even though it has fewer protons, fewer electrons, fewer neutrons, but it is larger because lithium and fluorine are in the same energy level, so we haven't changed the energy levels. Fluorine has more protons, and therefore there's a stronger Zeft, stronger effective nuclear charge for fluorine. And so the electrons around fluorine are pulled in tighter. They're more attracted to the nucleus of fluorine. It has more protons. They're pulled in tighter. And as a result, fluorine is actually smaller because of the higher effective nuclear charge. Now listen for a minute. I would actually write this down in a note card. All trends going from left to right across a period, every single trend, can be explained by the fact that you are adding more protons as you go left to right, and therefore the effective nuclear charge is increasing. All three trends that we're going to talk about can be explained that way. As you go left to right, you add more protons, and therefore the effective nuclear charge has increased. Let's try another one. If this was a mini essay question, let's see if you can answer it. Which is larger, arsenic, which has a symbol of AS, or sulfur? So look where they're located in the periodic table, and of course I'll give you a hint here. They're in the same family or group, vertical group. Sulfur is towards the top, arsenic is farther down. So which one is larger, and maybe more importantly, why? Here's the answer, and here's also a tip. This is really important. First of all, arsenic is larger. It's farther down. It's in a lower period on the periodic table than sulfur. And because of that, its outermost electrons are in a higher energy level, which of course is farther away from the nucleus. So here's the important thing. Every single trend going from top to bottom down a group, every single trend can be explained by saying the outermost electrons on the element that's closer to the bottom of the periodic table are in a higher energy level and therefore farther away from the nucleus. So we have exhausted atomic radius, which is a measure of size, and we're going to talk about ionization energy now. First of all, understand what ionization energy is. It's basically the energy required to turn a neutral element into an ion. And how do you do that? By removing an electron. So ionization energy is the energy required to remove an electron from an atom. Now, I want you to imagine a Bohr model of an atom with the energy levels, and imagine trying to snatch a valence electron away from that atom. First of all, that electron is not really going to want to be snatched away because it is attracted to the nucleus. And so it's going to take a certain amount of energy for you to snatch it. What's going to make it easier or harder for you to steal an electron from an atom? Well, the larger the effective nuclear charge is, the larger the effective nuclear charge that the particular electron experiences, the harder it will be to remove it. So one variable that can affect the effective nuclear charge is how far away the electron is. Okay? So the farther away it is, the easier it is to snatch it. So if you are at the bottom of a group on the periodic table, it's going to be relatively easy to take an electron away because those electrons are in a really high energy level, really far away from the nucleus. So ionization energy decreases, as you would expect, going from top to bottom down a group, because you're getting farther and farther away from the nucleus as you get toward the bottom of a group. All right, ionization energy increases moving left to right across a period. What does that mean? If ionization energy increases, that means it's harder to remove an electron. It's more difficult as you move left to right across a period. Why would that be? Remember I said you can explain every single trend moving left to right across a period the same way, and that is by saying as you move left to right across a period, effective nuclear charge increases because you are adding more protons, and therefore there's a stronger attraction to the electrons and they're harder to remove. If you need to replay that, go ahead. There will be a short essay type on your test about periodic trends and asking you to explain them, so make sure you can do that. Ionization energy is a little trickier. So the general trend is that it does increase left to right, as I said, because effective nuclear charge is increasing, and it does decrease from top to bottom down a group. However, there are some anomalies. So let's look at period 2. So in general, ionization energy increases left to right. So let's look at period 2. So in general, the ionization energy is increasing, going from lithium to beryllium to boron to carbon and nitrogen, oxygen, fluorine, etc. But there are some anomalies. You see how it goes up and down? It does not go steadily up. So let's look at where the weirdnesses are. One of the weirdnesses are between comparing beryllium and boron. Seems like boron should be higher than it is, right? Or beryllium lower. And the other weirdness is between nitrogen and oxygen. Oxygen seems to be lower than it should. We will explain these anomalies in a couple slides, but I want to test your general knowledge about the trends. Here's a typical multiple choice question about ionization energy. Look at the following elements and tell me which of these has the highest ionization energy. Which of these has valence electrons that require the most energy to remove? So I would pause the video, look at a periodic table, and see if you can give that a guess. If you picked helium, you're correct. But let me show you. All right, let's look roughly where all of these elements are located. It's hydrogen, helium, top left and right corners. Let's see, radon is down here. Rhodium. And let's see, francium is in the low left corner, and rhodium is somewhere in the middle. All right, so let me show you an easy way to get trends and then explain it a bit. So if ionization energy increases going left to right across a period, and ionization energy decreases going down a family, where is the element with the highest ionization energy? Right here, helium. So there's your answer. But the reason I'm showing you that is because, first of all, where's the element with the lowest ionization energy? Right here, the opposite corner. So ionization energy goes from left to right in a diagonal towards helium. So you can kind of tell by looking at that diagonal where the ionization energies of different elements lie. It's going to be a little fuzzy sometimes, but I'll give you ones to pick from on your tests that are pretty clear. All right, so here are the anomalies I mentioned earlier. If you look at any element in 2A and then any other element next to it in 3A, you will notice that ionization energy goes down between 2A and 3A, which is not what it's supposed to do. In general, ionization energy is supposed to increase left to right. And the same anomaly is seen comparing nitrogen to oxygen or any of the elements below nitrogen and oxygen. So let's go ahead and see why that is. If you look at the electron configuration for beryllium and boron, we're comparing those two. Notice that beryllium ionization energy removes the outermost electron. So with beryllium, we're trying to remove this electron. Okay? When we do remove it, we get the beryllium cation and we get an electron configuration that looks like this. Now, in doing so, we have broken up a full sublevel, the 2s sublevel. We've broken that up. Now, you might remember me saying in the last lecture that there's a lot of stability to be had with a completely full or even completely full orbitals are the most stable. So you've disrupted that when you ionize beryllium. Let's look at the element right to the right of beryllium, boron. Boron's the one that had an unusually low ionization energy. So let's look at that, why that may be. With boron, when we pull out the first valence electron, it's a 2p electron that's all by itself in the 2p sublevel. By removing it, not only does boron not really care that we've removed it because there was only one electron in that orbital, it's actually quite happy as a cation because now by removing the lone p electron, boron now it ends in a completely full 2s sublevel, which is very stable for it. So it is very easy to ionize boron and all of the elements below it. It's unexpectedly easy because they end up with this full sublevel when you remove the electron. So that explains that anomaly. Let's move on to the anomaly between nitrogen and oxygen. It's a similar explanation. If you were to draw out the electron configuration for nitrogen and you remove the outermost electron, you would end up with a nitrogen cation that looks like this. Well, do you think that costs quite a bit of energy, more than expected? It actually does, because nitrogen, when it's neutral, has a half-full 2p sublevel, which is quite stable. And by removing one electron, you have disrupted that half-full sublevel. So it costs quite a bit of energy to ionize nitrogen. Oxygen, which is to the right next to nitrogen in the periodic table, when you remove oxygen's valence electron, you end up creating a half-full 2p sublevel, which is a very favorable thing. So the ionization of oxygen is unexpectedly low, or it's easier than expected to remove an electron from oxygen because the result is a half-full sublevel, which is quite stable. Now, up to now, we've only talked about removing the outermost valence electron. Of course, there are things called second ionization energy, third ionization energy, fourth ionization energy, and that's just removing additional electrons. And of course, it costs more and more energy to remove more and more electrons, but that can happen. But removing electrons one by one in an atom tells us a lot about the element we're dealing with. If it's an unknown and you're trying to identify what it is, doing so through sequential ionization is very helpful, and let me show you why. It is relatively easy to remove valence electrons. Okay, depends on some other things, but it's relatively easy to remove valence electrons. It is extremely hard, extremely difficult to remove core electrons. So depending on how many valence electrons an element has, you'll be able to pretty easily remove that many electrons. And once you get all the valence electrons removed, you're in for a huge fight if you try to remove any of the core electrons. Here's a chart that demonstrates that. So sodium, for example, in its neutral state has one valence electron. So it's relatively easy. It still costs energy, but it's relatively easy to remove that one valence electron. But since it only has one valence electron, once you remove that, it's going to fight like heck to try to keep you from removing any more electrons, because what's left are core electrons. As a matter of fact, it costs you 10 times more energy to remove one of sodium's core electrons than it did the one valence electron. And that's the case for all the elements. So again, if you have an element that you're doing ionization energies to, and you don't know what the element is, wherever you see that huge jump in energy requirements would typically be when you reach the core. So let's skip down to silicon. Silicon's right under carbon. It has 4 valence electrons. And so relatively easy removing the first 4 electrons because it has 4 valence electrons. It gets a little bit harder with each progressive one, but only by 50% or something. But now, when you get to the 5th electron, now remember, silicon's in group 4A, it has 4 valence. So once you've removed these first 4, you're left with a core electron. Look what happens to that. The energy required to remove that first core electron is 4 times higher than the energy required to remove the 4th electron, which was still valence. So wherever you see that big jump tells you how many valence electrons an element has. So let's look at this and say you don't know what this element is, but I gave you a chart of all these ionization energies and said, how many valence electrons does this element have? Well, the ones that are only increase by a little, 50% or something, are typically valence electrons. Now, when you see a jump in energy that's typically more than a factor of 2, it can be a factor of 3, 4, even as high as 10 sometimes, that means that your valence electrons have been all removed. So how many valence electrons does this sample have? 1, 2, 3, 4, 5, 6. 6 valence electrons. So you could say, okay, this element is probably from group 6A. Here's a question for you to try on your own without my help. Look at a periodic table. Obviously, all of these questions about periodic trends, you need to have the periodic table in front of you. And compare potassium with calcium. Okay? Which element would have the greater difference between the first ionization energy, the first ionization energy and the second ionization energy? Okay, where would you expect to see a huge jump between the first and second? With potassium or with calcium, and why? I hope you get the gist at this point that depends on how many valence electrons. So you would need to identify potassium is in group 1A, it has 1 valence. Calcium is in group 2A, it has 2 valence. So the jump in ionization energy for potassium would be after you removed the 1 valence electron. In other words, between the first and second ionization energy. Calcium has 2 valence electrons, so it would be pretty easy to remove the first 2 electrons, but at that point, there are no valence electrons left, and you're down to the core electrons when you try to get the third one. So that's where the big jump would be for calcium. The final periodic trend that we're going to talk about is electronegativity. Electronegativity is basically the pull or attraction that an atom has for extra electrons. That's a property that's important when an atom starts to bond with another atom. Basically, that atom, if it's sitting there with a high electronegativity, that means it has a very strong attraction for additional electrons that perhaps another atom can provide. So the trends for electronegativity increase as you go from left to right across a period. They get more and more electronegative, and there are not the funky anomalies that you have with ionization energy. And electronegativity decreases going from top to bottom down a family. So let's think about what that means in practical terms. What that means is that elements to the far right have a higher electronegativity or higher attraction for more electrons. So that would be fluorine. It turns out that fluorine has the very highest electronegativity of any element. Its electronegativity on the kind of arbitrary scale we have is 4. Every single other element in the periodic table has an electronegativity of less than 4. The lowest electronegativity on the periodic table is francium. That means francium really has no desire for extra electrons, and in fact tends to give away its valence electrons. So you could write this trend with a diagonal arrow to show electronegativity. Let's summarize the 3 trends. I strongly recommend drawing this image on a note card or in your notes and committing it to memory. I've emphasized from the beginning that I want you to understand the explanation for them, but of course you also need to know what the trends are before you can explain them properly. So first of all, I am not going to hold you responsible for metallic character, but I have seen those questions on the periodic table. So let me just point out, where are the metals located on the periodic table? Well, they're to the left of the stair step, right? Okay, these are all metals. So of course the metallic character is going to increase as you go toward the metals and decrease as you go to the non-metals. So just there for a tidbit. All right, so the 3 periodic trends that we've learned about are atomic radius, okay, and electronegativity and ionization energy. Take a look at those 3 trends. Do they go in the same directions? Do they go in opposite directions? And hopefully you can see that ionization energy and electronegativity are buddies. Their trends are always in the same direction. Atomic radius, on the other hand, I always thought of it as the rebel, goes in the opposite direction than ionization energy and electronegativity. All right? If I asked you for the largest element, you should be able to say it's francium. If I asked you for the element with the highest electronegativity, it would be fluorine. Now, you may have noticed that I have conveniently left off the noble gases in talking about electronegativity. That's because, for all practical purposes, noble gases have 0 electronegativity. They have full outer shells, they're extremely stable, they have no desire to take on any extra electrons or to really get much involved in chemical reactions at all. So that's why fluorine is the highest electronegativity. What is the element with the highest ionization energy? That would be helium. Now, the noble gases do have ionization energies. They're going to fight like heck if you try to remove one of their electrons. So they tend to have very high ionization energies. So that is it for periodic trends and for Chapter 8. There's really not much math. There's no math in Chapter 8, but there are a lot of concepts. There are going to be some short essay questions, so focus on the concepts in Chapter 8 and the math problems in Chapter 7.